Okay, let's take a look at the definition of summation notation. Occasionally, when you're working with sequences and series, we want to be able to quickly add up terms of that, and so finding the sum of that becomes very important. And so notationally, we want to write it as condensed and concisely as possible, and the summation notation allows us to do it. So if we're adding up the first n terms of a sequence, so we have term 1, term 2, 3, 4, all the way up to whatever that nth term is. First of all, we want to be able to express that entire sequence in a very concise way. That's that AN notation that we had earlier on. And so what we're going to do is this. We start with, in this case, the first term. We're adding up to the nth term. So we say, all right, let's start with 1. So we're going to call that the lower limit of the summation. And we're going to add up all the way to n. That's the upper limit of summation. And I is the variable of choice that we're using here. Before it was a sub n. Here it's I, just so that it's a different variable than the n that's there. I also stands for index, but quite often they use I, they use j, sometimes k. Theoretically, we can use any variable that we want to do. All right, so let's take a look at some examples here. So example A, calculate. So what we're doing is we are adding up a bunch of sequences or a bunch of terms that look like 3 times something. And we're going to let that first something be 1, and we're going to add all the way up until that something gets to 5. So let's go ahead. This is the Greek letter sigma. That's the Greek letter for S. And so it's going to be 3 times 1 plus 3 times 2. And we're going to just keep substituting numbers. We increase by 1 every time until we get up to 5. Now, however you want to add these is totally up to you. I'm going to go ahead and do it in a certain way that's going to lead to some of the stuff we'll talk about in just a moment. Notice there's a common factor to each of these terms, that 3. So that would, if I took that out, that would leave me 1 plus 2 plus 3 plus 4 plus 5. Now we can add up those, and we get 15. And 3 times 15 is 45. Second example, we are adding up k equals, and we're starting with 3 this time, up until 6. And that is going to be terms that look like 1 plus something squared. So we have 1 plus, and our first k is 3, plus 1 plus our second k is 4. Our third k would be 5, all the way up to 6. Again, I'm going to do something here. Notice all of these are additions all the way across. So I'm going to gather those ones. You can see that we have 4 ones. And then I'm going to go ahead and square. So we have 3 squared, 4 squared, 5 squared, and 6 squared. So that gives us 4 plus 9 and 16 is 25, plus 25 is 50, plus 36 is 86. 4 plus 86 is 90. All right, the third one is, and you can see it on your papers in front of you, it's a sum from n equals, this time we're starting with 0, and we're going up to 8, and it's 1 over n factorial. So we start with 1 over 0 factorial, plus 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, and I'm going to go ahead and do this, plus so on and so forth. The pattern has clearly been established up until we get to 1 over 8 factorial. All right. So now what I want to do is this. I want to go ahead and show you how to do this on, especially if you have a TI calculator. So let's go ahead and we'll bring up our TI calculator. The summation is under this math button. So we hit sum and we scroll down or up if you wanted to. And down here at 0, we have the summation. And they want us to choose a variable. The only variable we have is this x button. So we're going x equals 0 up to 8 And in here we have a fraction. The fraction key, we hit alpha, y equals, and then number 1 is our fraction. And it's 1 over x, and now we need the factorial. The factorial, we're going to go ahead and hit math button again. And now this is a probability concept, so we're going to go over to probability. And down there at option 4, we see the factorial. Okay, so our summation from x equals 0 to 8 of 1 over x factorial, we hit enter, and we get 2.7182787. So again, we get 2.718, and that's good. All right. Now this number here should look familiar. Okay, this number is almost e. Okay. In fact, if I come back in here and I type just e, we can see that actually is pretty close. Okay. And in fact, if I were to increase that 8 and go up higher, 9, 10, 20, 100, 1,000, then it would just get closer and closer and closer to e. Okay. This note here, again, the lower limit doesn't need to be denoted by I. And by the way, I should actually go back in here and, well, no, it's n anyway in the problem. So good. All right. Here on this next page at the top, you see exactly just a reminder of where the summation and the factorial buttons are in your calculator if you need them in the future. Now, properties of sums. First of all, the sum of a constant, C is a constant, is just however many terms you have times that constant. And we saw that back in example B up here. Notice this is now this is part of a sum. We'll talk about that in just a minute. But we had a 1, which was just a constant, and we ended up with 4 1s, which if we count from 3, 4, 5, 6, we have 4. Okay, so the sum of a constant is always just going to be that constant times however many terms there are. Okay, if you want just a quick example, the sum from I equals 1 to 5, that would be 5 terms, of just, let's say, something like 3, is just going to be 3 times 5, or 15. 2, the sum of a constant times a sequence. That constant, in effect, just gets pulled right through the summation, and we can put that out in front. That is, I can do the summation of all the terms, and then I can just multiply that by c. And we even saw that up here in example 1a, where that 3 kind of gets pulled out, and then we just add up those previous terms. So I could have written this as 3 times the summation from I equals 1 to 5 of I. And that's why I pulled that 3 out earlier. And then the last two is a kind of a modified distributive property. It just says this, that if you're summing a sequence that is actually itself a sum, that we can in effect distribute, and we can distribute as well over subtraction. And that is, you can just sum the different terms. And again, we saw that as well up here in example B. When I had this term here, because it ends up being all addition, we can just add up that first set of terms, and then we can add up that second set of terms. So I could have written that sequence as the sum from k equals 3 to 6 of 1 plus the sum from k equals 3 to 6 of k squared. This here, there's 4 terms. It would just be 4 times because this is a constant. And this here, there are formulas for this, which you may learn later on. But this here, at this point in time, we would just go ahead and do the math out. All right, we have one more section. I'll do that in the next video.